Last time we said that there are three main cases of harmonic forcing on single degree of freedom systems. Last time we covered the first case, the direct forcing, in which the force directly acts on the mass, and force is a sinusoidal force. Here in this case, today we will be covering the rotating unbalance, in which there is an unbalanced force acting on the mass. It might seem to be very similar to the first case, but the difference comes from the fact that the amplitude of the force is dependent on the frequency. Let's try to show that. In rotating machines, is a common source of vibration is the unbalance. Let's say that you have a machine such as an electric motor in which there is a small unbalance. Okay, in that case, that unbalance keeps on rotating, and as it rotates, it creates a centrifugal force in the direction, in the outward direction. What we are interested is the vertical vibrations of this machine. So in that case, we will be looking at the vertical component of that force, which will be me omega squared sine omega t. Small m is the mass of the unbalance, and E is the eccentricity of the unbalance. So me is in total mass times the eccentricity. It is called the unbalance. So the force acting, vertical component of the force acting on the system is me omega squared sine omega t, is the effective force acting on the system. And if our system has again a mass spring and damper, here the mass of the system is shown by capital M, and small case m is the unbalanced mass. In this case, the equation of motion of the system will be given by the following differential equation. And if you look at this differential equation and compare with the previous case of direct forcing, we see that the amplitude of the forcing, which is F0 in that case, is equal to me omega squared. So all the results we have derived, assuming that the force is F0 is, if the F0 is replaced by me omega squared in all those results, the results should hold. But as we will see, the picture of the frequency response will change because of the fact that F0 now is not a constant, but it's a function of omega squared actually. So if we look at our equation, me omega squared is F0, remember. So we have F0 over K divided by square root of 1 minus R squared plus 2 zeta R squared. This is the magnification factor, okay? So this M over K, as you remember, is omega n squared. So if I try to write it, M over K is 1 over omega n squared. So you have omega, I'm sorry, this should be the capital M over K. I will multiply this by M and divide it by M. So this capital M over K is going to be 1 over omega n squared, and this M over capital M will stay here, in which case this omega over omega n squared becomes an R squared, as you know, and here we will be having M over capital M divided by E. So the amplitude of vibration here is going to have a R squared term in the numerator of the amplification equation. Okay, in the direct forcing case, we didn't have this, and this has certain consequences as we plot the response, as we plot the frequency response of our system. The phase angle remains the same, but the non-dimensional plot of M capital X, capital M times capital X divided by ME, which is a non-dimensional quantity, versus R, comes out to be a picture like this one. It starts from 0 because of the fact that now you have an R square in the numerator. Also, eventually, for the very high frequencies, it goes to 1. That is mx over me goes to 1. Whereas in the picture of the direct forcing, this was different. It had started from 1, went up at resonance, and went to 0 at very high frequencies. So the shape of the curves are different, but the general structure is more or less similar. There is still a resonance in all of those curves. That is, there is a peak point at which the amplitude becomes a maximum. So if we look at these pictures, we can make the following conclusions. As I have said, first of all, for omega equals 0 for low frequencies, that is for the very low frequencies, such as here, this is omega equals 0, and this is omega is high, let's say. In this case, the amplitude is 0 for 0 frequency, for all values of zeta. When the omega goes to very high values, or R goes to infinity, as we have said here, all the curves go to 1 independent of zeta. And the maximum value of the rotating unbalanced response can be found from taking a derivative of this equation with respect to R. And the result is very similar to the unbalanced, the direct forcing case, in which case the maximum frequency is equal to 1 over in square root 1 minus 2 zeta squared. So the resonance frequency, again, is the same with our previous case. It is omega resonance is equal to omega n 1 minus 2 zeta squared again. And the maximum value can be obtained, maximum value of this curve can be obtained by substituting this value of R into that equation. And what we get is exactly the same as the direct forcing case, 1 over 2 zeta in square root 1 minus zeta squared. And we can say that this is also approximately equal to 1 over 2 zeta if zeta is small. Okay. And also, if we look at these curves, after a point, our curves, after the damping is increased to a certain value, the curves have no maximum anymore. After the point of zeta equals 1 over root 2 or 0.707, the curves have no maximum at all. So they don't have a peak like a resonance. So for very high values of damping, there is no resonant peak in the frequency response. I will conclude this by giving a very simple problem. Let's say that you have an industrial machine that operates at 125 hertz, and it has a rotating unbalance. This rotating unbalance is mass times the eccentricity. This is ME, 0.15 kilogram meters. The machine is mounted on a foundation with a stiffness of 2 times 10 to the 6 Newton meter, and it has a damping ratio of 0.12. So we want to determine how much the amplitude of the machine is. We start by finding the natural frequency of the system, which is root k over m in square root. So if you find it, it is 175.4 radians per second. Now the frequency of excitation is 125 hertz, but we have to convert hertz to radians per second first by multiplying by 2 pi. So the omega is 125 times 2 pi, and the R value, the frequency ratio, is omega over omega n, so it becomes 4.48, which is a high number. So if you look at your curve here, you are somewhere around here, in which the curve is almost equal to 1, almost independent of damping. So the steady state amplitude of our response can be found from r squared divided by square root of 1 minus r squared squared, 2 times zeta times r squared. And we find that it is 1.05, very close to 1. Now the response is not this one, but it is the capital X. By the way, M0 is the total mass of the machine. 0.15 is the eccentricity. M0, yes. So this part we have found it, by the way. This part is the thing we have found before. This is 1.051. We just have to multiply it with M0E. M0 is the eccentricity times the E, divided by M, which is the mass of the machine. So we multiply it and we get the result as 2.43 millimeters. So the machine, why